end, but kind of the last section here is on heating and chemical effects. This is another good section to improve your mark on. So we started. Okay, so where did we start? We started with basically with Q. All right, and then from Q we got the. Well, actually, we started. Probably look at it like this. We started with electrons, then we became Q, then we became I, and now, bless you, we're going to end up with power. Okay, so that's where our intentions are getting to is what, because when we measure our hydro off of our house, all right, we are measuring the amount of power, the amount of watts that we use throughout the amount of time, the period of time in which we are measuring per month usually. Okay. All right. So we started with, and what I'm going to do is I'm going to give you a list of equations that you're going to want to check off. All right. So W equals Q over V, or Q times V. So that's work is equal to the charge times the potential difference. So 1 joule of work is done when 1 coulomb of charge is moved through the potential difference of 1 volt. Okay, so 1 joule is 1 coulomb volt. All right, 1 coulomb of charge transferred in 1 second constitutes 1 ampere. So we work in current now. So we are going to join a bunch of equations together. So we've got to see where they start and how we get to them. Okay, so work is equal to QV, I is equal to Q over T. Q then, from this guy, is I times T, in which T is the amount of time in seconds. All right, so we'll make a note of that here. T is time measured in seconds. So I can then find, by substituting in for Q here, I can calculate work by taking the potential difference times the current times the amount of time. Now I generally use a little t. I generally use a little t for time because we're actually going to work with temperature as well. So I use big T for temperature, although they use big T in there. As the charge moves through the external circuit in response to the potential difference across the circuit, work is done by the electrons on the components of the circuit. Work is done as a light, lamp, rotary motion, electric motor, chemical action, electroplating, heat. Okay? Energy conversion in resistance. All right, so now we've got work is equal to VIT. We also know from Ohm's law that V is equal to IR. So depending on what we are given, we can calculate work in 3 different ways. All right? So work is equal to, so if I've got V times I times T, and let's say I don't know what V is. Let's say I only know my current and my resistance. Okay? So I'm going to substitute IR in for V here. Well, that's going to give me I squared RT. So there's equation number 2. Let's call that equation 1, equation 2 for work. Work equals. All right. So now we maybe don't know what the current is. We only know what the volts and the resistance are. So my current is equal to V over R. So when I substitute it in VIT, I get V squared T over R. So that would be your 3rd equation. So that's if I know voltage, time, and resistance, and I don't know current. Now at any one of these points, you only need to use equation 1 if you're working with V equals IR, because you can always find the other ones. Okay? So these are 3 new equations to help us get to work. All right. We talked about Ohm's law being V equals IR. Today we're going to look at the second page. There has Joule's law. So we are going to take now work. We're going to find out how it relates to heat, and then we're going to find out how it relates to power. So Joule's law, the heat developed in a conductor is directly proportional to the resistance of the conductor, the square of the current, and the time the current is maintained. So the heat developed in a conductor is directly proportional to the resistance of the conductor, the square of the current, and the time which it is maintained. So that is actually works off of this guy right here, V squared T over R. Or I squared RT. That's what it works off of. All right, so electric energy expended in the resistance is directly proportional to the heat energy that appears. So a new equation here. Work is equal to J times Q. Now Q is not your charge anymore. Capital Q is the quantity of heat, which we measure in calories. Q is the quantity of heat in which we measure in calories. J is Joule's constant. So that's a value. When you have a constant, the value doesn't ever change. So it's 4.19. And the units are joules per calorie. J equals 4.19 joules per calorie. So technically speaking, Joule's law is referring to the amount of heat. It can be found by taking the amount of work divided by Joule's constant. Now, we're going to use some of our work equations in order to get this. So to find the amount of heat energy, the first one we're going to work with and the primary one we're going to work with is this guy. We aren't going to work with potential difference. We're going to work with current and resistance. So I squared RT over J. Okay. Let's look at the third page. So before I get to the actual question, those of you in chemistry or have done chemistry probably worked with heat, with specific heat constants. All right. So the amount of heat required to raise a mass above a substance, that much temperature in Celsius. So Q equals MC delta T. M is your mass of your substance that you're warming. T is how much temperature change there is, hence the delta T. And then C is the specific heat constant. That is found on a chart in the back of your book. It's in that 676 range, 675, 674. So that's called the specific heat constant. So every substance has a different specific heat constant for the amount of heat required to raise the temperature of 1 gram, 1 degree Celsius. Okay? Or in most cases, it'll be 1 kilogram, 1 degree Celsius. So there's two different Qs. This one is for specific heat constant. This one is for power related. So when you plug in what we're going to look at today, or as we go through over the next couple of days here, we're going to look at the heat efficiency of a heating element. How efficient is the heating element? So we're going to find out how much we input, how much power we input, or how much heat we input to it. And then we're going to find out how long it takes to raise the temperature. And then we're going to find out how efficient that heating element is. So we're going to get to that. But first question here says a heating element in a percolator, so basically a kettle that you plug into a wall, has a resistance of 22 ohms. So the first thing that you're going to do today is learn how to write out all of the information. So we want to write out 22 ohms. It's designed across a 117 volt circuit. How long will it take? How much time will it take to heat 1 kilogram of water? Now, I'm going to make a suggestion to you today. I think it's far easier to work with grams and change to kilograms and kilocalories after the fact. So we'll convert everything to grams today. So 1 kilogram of water, so that's 1,000 grams of water at 20 degrees Celsius to the boiling point of 100 degrees Celsius. That means my change in temperature is 80 degrees Celsius. Okay? So what we are wanting to find is the amount of time required to heat that amount of water. So what we have to do then is we have to look at these two equations that we wrote down here and see what we're given. So I want time. So I have to use Q equals I squared RT over J. And I want to solve for T. So T is equal to QJ divided by I squared R. Okay, so all I did was arrange to get time by itself. Times the J up, divide by I squared R. So what information do I need to know in order to solve for the time here? What are the 4 pieces of information I need to know? Current, resistance, joules, well, resistance, heat. Okay, so so of this information, looking on the board right here, so looking over here, of that information, what do I know so far? I should have added this in here. So I've got 4.19 joules per calorie. Okay. Joules per calorie. Now, there is one other piece of information I didn't write in, and I have to write this one in. Go to the back of your book right now. So take your textbook out. Go to the back of your textbook, like 674-ish, somewhere in there, 675. Look for the chart that says specific heat constants at the top of the page, at the top of the table. You can do that too. Specific heat constant.
I found just straight heat constants.
Okay, that'll work. Actually, you can use this. Just don't take it with you. Leave that in here because that's my only teacher edition. What do you got?
674.
Heat constant? Okay, go down there and find what water is. One what? What are the units on it?
Oh, J per G times C. Right?
1 joule per gram degrees Celsius. Okay, so what does that mean? Is that what it is, joules? I actually don't like that. Yeah, it's right, but it's funny. I don't want to use this one. I forgot. I actually want the calorie one. I think it's the same thing, but say 674. One, yeah. I'm going to change this right here, right now. Okay, we are going to use 1 calorie per gram degrees Celsius. Okay, so what that means is this. I need to apply 1 calorie of heat to raise the temperature of 1 gram of water 1 degree Celsius. That's what that specific heat constant means. I need 1 calorie of heat to raise the temperature of 1 gram of water 1 degree Celsius. Okay? So, again, I go back up there, and what do I know? Do I know J? Yeah. Do I know R? Yeah. Do I know I? Okay, let's make that the first thing we find. So to find I go I equals V over R. Do I know what my V is? What's my V? 117 volts divided by 22 ohms of resistance. Okay, so take 117 and divide it by 22. 3 decimal places.
5.318.
So I have 5.318 amps. Okay, so now I have my J, which is 4.19 joules per calorie. I have my I, which is 5.318 amps. I have my R, which is 22 ohms. Excuse me. The next thing I need to find is my Q. So to find my Q, I'm going to use MC delta T. What was the mass of the water? Specific heat constant. And my temperature was how much? What was my change in temperature? 80 degrees Celsius. Okay. So what does that give me? What's my heat? $80,000 calories. Okay? Good so far? Now I need to find out how much time it's going to take to raise the temperature of 1 kilogram of water 80 degrees Celsius. So let's put that into our calculator. Time equals. So Q is 80,000. J is 4.19. Divided by, you need to have brackets on the bottom. 5.318 squared times 22. Close the bracket.
538.747.
747?
That's what I got.
Perfect. Thank you. Seconds. So it's going to take 538 seconds to raise 1 kilogram of water 80 degrees in this percolator. Okay? Any questions? Pretty straightforward so far. Okay, now what we're going to do, we're going to look at the power equations now, because that's our end game. So let's look at the power equations, and then from there we'll be done, and that's all we really have to learn for this unit. It's a shorter unit. It's a good unit. Okay, power, by definition, is the rate of doing work. The rate of doing work. So that means the amount of work over time. Power is equal to W over T. We measure power in watts. Often we'll use kilowatts. Okay, so we're going to go back and we're going to do the same thing we did with work now, and we're going to substitute in our other equations for it. So power is equal to VI over T. Work again is V times I. There's a problem with that. Hold on. 18.4. Page 452. No T here. My bad. Power is just equal to VI. No T there. Because work over time was equal to VI. Work over time was equal to VI. So power is equal to VI. So now, if I again use Ohm's law, if I don't know V, this becomes I squared R, or V squared over, what is that? I would be V over R, so it'd be V squared over R. So there's your three power ones. Those are your three power equations. Okay, now, there is one important thing that we need to know about power. So we are going to still work with circuits a little bit. Not as complicated circuits, but we're still working with circuits. And what we're going to do is we're going to add in to our table power. Okay? So the circuits aren't going to be as complicated, but we're adding in power to it. So you're going to have an extra column now. Second, this is the most important part. In order to get maximum power to the load, make a note of this. Maximum power to the load. The internal resistance has to equal the load resistance. In order to get maximum power to the load, you have to switch out your load resistance so that it is equal to the internal resistance. Maximum power to the load. Transfer maximum power to load is important. An example is starter motor of an automobile engine. You want maximum power is transferred to the load when the load resistance is equal to the internal resistance of the source of EMF. So if I'm looking at proving this, okay, let's say I have a 3-volt battery.
Let's write this down.
No, this you don't need to write down. Okay, so let's say I have 3 volts here. I have an internal resistance of 0.5 ohms, and I have a load resistance of, what did they put their load resistance as? 1 ohm by the looks of it. Okay, so the load resistance has a greater resistance than what the internal resistance does. So if I'm looking at the power then, okay, so let's do it just like this. V, I, R, P, R, R, L, R, T. Okay, hold on. Let me clean this up. Might as well do this. No point. I. Okay. So again, I said back to this. Little R, R, L, R, T. Okay, so my total voltage is 3 volts. 0.5 ohms, 1 ohm. What does that make the total ohms? Total ohms, 1.5 ohms, which makes the current 2 amps, right? So let's just fill in the rest of this information. So everything else has 2 amps. There's 2 amps here, 2 volts, 1 volt. So far, so good, right? Let's check the power on it. Okay, so
Total, right?
6 total, V times I, 6 watts, right?
2.
2 watts, 4 watts. Okay. Now, I'm just gonna do this. Here.
So is power like the last thing you're gonna do when you do the?
That's not gonna work. Okay. So now I'm gonna change this up. Again, I'm just gonna use this to. So our intended goal is to get the maximum power to the load resistance. That's our intended goal. Okay, so now I'm gonna make, in the second one, I have the load resistance is smaller. So I have 0.5 ohms here, I have 0.1 ohm here. Okay, still have 3 volts. What is my total resistance? 0.6 ohms, okay? Total current,
1.5.
5 amps.
Oh, what? No. 0.6 times 3 is 1.8.
Is it times 3?
Yeah, 1.8. Oh yeah, it's divided, sorry.
So what is it?
5.
5 amps, right. So I have 5 amps,
Oh,
5 amps. Okay, so 2.5 volts, 0.5 volts. So that's where I'm at. Okay, now let's look at the power on the outside. Sorry?
no, it's got that.
Okay, so now I have V times I. What's 2.5 times 5?
12.5.
Oh, yeah, 12.5. Oh,
Bad day for math.
Oh.
tough day. Tough day.
Price good.
Isn't it Monday? So 12.5 watts. Okay, now I got 0.5 times 5. So the power in this is only 2.5 watts for a total of 15 watts.
Brutal day.
15 watts. Okay. So total power in the load is still less. That doesn't give me my maximum power. So now what we're gonna do is we're gonna check this a 3rd time, and this time we're gonna make the power let's make the power and the internal resistance equal. Let's see what happens here. So I've got R, RL, our total 3 volts, 0.5 ohms, 0.5 ohms, for a total of 1 ohm. Okay. How much current in the circuit? 3 amps. 3 amps. 3 amps. What does that make the voltage on all of these?
1.5.
1.5. 1.5 volts. Okay. All right. Now, when the resistance in the load was greater than the internal resistance, we got 4 watts. When the internal resistance was greater than the load resistance, we got 2.5 watts. So we had less power. Now what's going to happen?
Same power.
Same amount of power. The maximum power we can get is 4.5 watts, which is 9 watts. So in order to get maximum power, this has to match that. That's all that we need to know. That's it.
when things are in parallel, though, what's that, like, is the power gonna be the same throughout parallel, or it doesn't even matter? Like, when you go to add it up at the end?
Well, it depends if the resistances are the same. Okay, so you still do everything that you just learned in the last unit, you still do it the same way.
Yeah.
All you're doing is adding on power by finding V times I. So you do it the same way. But like I said, the circuits aren't gonna be more complicated. Okay, let's look at this last example question here. A small electric furnace connected across. Okay. So a small electric furnace connected across a 117 volt line. It's on page 6, I think, of your sheets. Yeah, it's on page 6. Okay. Power dissipates. I'm changing this again. I think it's best that we work in watts, grams, and calories. What is the current in the circuit? So we've got P, we've got V. We want to know what I is. So how do I find I?
Divide P by V.
Yes. So take 2,000 divided by 117. What do I get?
17.094.
Perfect. Thank you. There's your X. Okay. What is the resistance of the furnace? So let's do this again. I want resistance this time. How would you find the resistance? Okay, now that's right. You would use the VIR part. That's okay, but what happens if I made a mistake on it?
Then you're wrong.
Then I'm wrong a second time, right? So why don't we, what is the relationship between P, V, and R? Look at your formulas. P, V, and R.
P equals I squared.
I don't want the I part. Okay. This is what we started with, right? This and this. So how about we get rid of the I in this equation? So I'm going to get I equals what in here? That, correct? So if I substitute that into here, I get V times that. So what does power equal? V squared over R. So take 117 squared. Oh, sorry, I want resistance, right? So my resistance here then, so let's go down here. P equals V squared over R. Therefore, R is equal to V squared over P. So take 117 squared and divide it by 2,000.
One second here.
6.844 or 845.
Okay, so I've got the current, I've got the resistance. What's the next thing that's asked of us to find? It says, what is the cost of operation for 24 hours at 10 cents per kilowatt hour? Okay. So this one's different. We haven't looked at this yet. This is where we're getting at. So 24 hours is the time, 10 cents per kilowatt hour. So I need to take the number of kilowatts, times it by the number of hours, and then times it by 10 cents per kilowatt hour. So we have 2 kilowatts. 24 hours
Times 10 cents.
times,
Or $2.
no, you're right first time. 10 cents per kilowatt hour. So how much is that? $4.80. Is that right?
Yeah.
2 times 24 times 10 cents. Okay. And the final thing is, what is the quantity heat in kilocalories that's developed in 1 hour? Okay. So now I'm going to change this to seconds. How many seconds are there in an hour? 3,600 seconds. Okay. So I want Q equals I squared RT over J. So again, I'm going to work with this in terms of calories rather than kilocalories. I need to change the time to seconds. So let's put this through. So I've got 17.094 squared. Resistance is 6.845. Time, 3,600 seconds. Divided by 4.19 joules per calorie.
That's just a constant no matter what.
That's right. It's called joules constant. Okay, so punch that into your calculator. Let's find out how many calories of heat that is. Okay, what do you got? Somebody give me an answer. Well, I have no faith in your ability.
I got
1.7 million.
I got 1 billion. I got 1 million.
Okay, we'll use your,
Oh, yeah.
what is it, 1 point what? Should give it to you in scientific notation, no?
1718499.181.
I got 1643181.67. Yeah, that's what I got. Two guys got that copy right. Or would you get? Same thing. Right on.
I'm putting brackets.
I didn't either.
$1,718,491 calories.
Wait, so how did we do it?
Divide by 1,000.
No, we did it right.
Divide by 1,000 to get how many kilocalories that is. So it's 1,718.499 kilocalories.
Did you use any brackets? That's probably why I grabbed it. That's where I went out. I put an extra 0 and 36,000.
Okay,
Probably what you said.
that's it. So for the rest of today, page 452 has 2 questions on it. All right, there's your assignment today. You'll do the group A questions. And all the problems. Group A questions and all the problems on 456. So that'll take us today and tomorrow. For sure.
Group A questions and problems. Yeah. So you said, yeah.
And